Now, let us see the general differential equation for heat conduction in cylindrical or polar coordinate. So here we can see that we have a cylinder here, and in the cylindrical coordinate system we have two linear dimensions and one angle. So the linear dimensions are radius r and height z, and the angle will be phi. So here we have a point in the cylindrical coordinate system. I'll call it as P, and that depends on R, phi, and Z. So now we are dealing with temperature. So instead of P, you can consider this as T. Now T is function of R, phi, and Z. So to derive general differential equation for heat conduction in cylindrical coordinate or spherical coordinate, what we can do is, as we have done in the Cartesian coordinate system, we can take a very small elemental area here of thickness dr, and then we can apply energy balance equation over the small elemental volume. And once we apply energy conservation equation, then we will get the differential equation. Or what we can do here is, so here we have shown the overlapping of the Cartesian coordinate system also. So we have x here, we have y here, and we have z. The z remains same for both Cartesian as well as polar coordinate system. So with the help of this, we can transform the polar coordinate or cylindrical coordinate system into Cartesian coordinate system, and we can use those transformation to draw or to write the equation for general differential heat conduction equation in cylindrical coordinate system. So what I'll do is to write the transformation. So here I need the value of x and y. I know z remains same, the height remains same for both Cartesian and polar coordinate system. So now I need to express x and y in terms of the other two parameters, that is r and phi. So if I look into this triangle, here this is the angle phi, and here I have x. So from here till here I have x. Now I need the value of x. So I know the hypotenuse, this is the right angle, so I know the hypotenuse is r, and I know the angle as phi. So now our x is, this is our x. So x is the adjacent side for this right angle triangle. So I can write cos phi will be equal to adjacent, that is x, divided by hypotenuse, that is r. Or I can write x is equal to r cos phi. Now I know that in the Cartesian coordinate system, the equivalent of x is r cos phi. Similarly, now if this is angle phi, this line is parallel to y axis, so this becomes our y. So now this is the opposite side, so I can use sin phi. Sin phi will be equal to opposite side, that is y, divided by the hypotenuse, that is r. Y will be equal to r sin phi, and I know that z will remain as it is in both the coordinate system. So with the help of these three formulas, that is x equals r cos phi, y equals r sin phi, and z equals z, I'll substitute the value of x as r cos phi and y as r sin phi in the general three-dimensional equation which we derived for Cartesian coordinate system. So if I do that, then I'll get the equation as 1 divided by r into dou by dou r of r into dou t by dou r plus 1 over r square into dou square t by dou phi square plus dou square t by dou z square plus qg by k will be equal to 1 over alpha into dou t by dou tau. So this equation is the general differential equation for heat conduction in cylindrical or polar coordinates. As I said, we have two methods through which we can achieve this. One is by considering a small elemental volume in this cylinder, and the second one is using the coordinate transformation system. So now let us look into the spherical coordinate. So in the case of spherical coordinate, we have two angles, that is phi and theta, and one linear dimension, that is r. So if you want to represent any point in a spherical coordinate, so the point P will be a function of r, phi, and so in this case we need temperature. So I'll rename this P as T. So if you want temperature, then temperature is a function of radius and two angles phi and theta. So theta is the angle of inclination of radius r with respect to z direction, and phi is the angle of the r projected on xy plane. So when you project r on xy plane, so whatever the angle that makes with respect to x direction, we call it as phi. Okay, now we can go for the first method, that is by considering an elemental volume and then deriving the general differential equation for heat conduction, or we can go for coordinate transformation. So in this case, the coordinate transformation are for x, it will be equal to r sine theta cos phi, and for y it will be equal to r sine theta sine phi. Let us see how we get this. So we have this projection on the xy plane, so that is the projection of r. So if I want to find out this length, then what I can do is, now this angle is theta, so this angle will also be theta. Now this completes a right angle triangle. So we have a right angle triangle here, and if I want the projected length of the projected line on xy plane, that is this length, then that will be, so r will be our hypotenuse. Here the angle, this angle is 90 degrees, so this is the angle theta. So this side becomes the opposite side, so it becomes r. So the length of this line will be r sine theta. So r sine theta will be the length of this line, and now this line is inclined to x line by an angle phi. So if you remember the previous case, it was r cos phi. So now it becomes r sine phi cos phi for x, and similarly for y it becomes r sine theta sine phi. Now we need to find out z. So z will be equal to, now we have this line, that is the radius. Radius is inclined at an angle of theta with respect to z. So if I want to find out the height, or that is z, then what I can do is I can draw a straight line here. So this angle will be 90 degree and this angle is theta, as we know. So since we know theta and I need adjacent side here, so I can write when it comes to adjacent side, we know that it is r cos theta. So r cos theta will be the value of z, and r sin theta cos phi is the value of x, and r sin theta sin phi will be the value of y. And this is the equation which you have to use for coordinate transformation. So now if you apply this equation in the general three-dimensional heat conduction equation which we derived for Cartesian coordinate, then we get the equation as 1 over r into dou by dou r of r square into dou t by dou r plus 1 divided by r square into sin theta into dou by dou theta of sin theta into dou t by dou theta plus 1 over r square sin square theta into dou square t by dou phi square. I'll continue here, plus qg by k will be equal to 1 over alpha into dou t by dou tau. So this gives us the general differential equation for heat conduction in spherical coordinate system.